there, it's Mrs. Scarpel, and we are going to start discussing section 3.2, linear functions. So last week we looked at what makes a function, and we are now going to focus our direction on linear functions. And you're probably used to talking about lines, and you know that a line is straight. In fact, I have a lot of students say, well, lines are straight lines. Well, that's kind of, how do I want to put it? When you say a line is a straight line, you're saying the same thing. All lines are straight. So with a linear equation, we have two variables usually. We're going to be focusing on x and y. Remember, x is our input and y is our output. So when we have two variables, x and y, we can write an equation in the form y equals mx plus b, where m and b are constants. Constants are numbers. So y equals mx plus b, and we will have numbers in place of m and b. And remember, y is the output, x is the input. A linear function is a function whose graph is a non-vertical line. Remember, a function must pass the vertical line test in order to be a function, and so a vertical line would not pass that test. That's why we include the definition of a non-vertical line with a constant rate of change. So as x increases by a certain amount, y is also increasing by a certain amount, or as x decreases, y is increasing or decreasing. And it can be represented with a linear equation. A nonlinear equation, or nonlinear function, I should say, does not have that constant rate of change, and the graph is not going to be a line. So let's just take a look at some graphs. Which graphs below represent a linear function? Well, we've said that a graph has to, in order for it to be a linear function, the graph has to be a line. So if your graph has any sort of curve, like this first one does, this is not a linear function. In fact, this particular curve is called a parabola. Here we do have a line. So this is a linear function. Here we are increasing, and it is a line. So we have a linear function. And the fourth one, we have a curve. Because it is curved, we do not have a line, therefore it is not a linear function. But we can also look at tables. And when we look at a table, we want to see, is it increasing the same amount or decreasing the same amount? So I'm going to look at my x values. So each of my x values here, from 2 to 4, I'm going up by 2. 4 to 6 is increasing by 2. 6 to 8 is also increasing by 2. Let's look at the y values. 9 to 18, increasing by 9. 18 to 27, also increasing by 9. 27 to 36, also increasing by 9. So as x increases by 2, y increases by 9. So we would say that yes, this is a linear function. Or I guess it's not asking if it's linear or nonlinear, it's asking if it's a function, or excuse me, it's not asking if it's a linear function, it's asking if it's linear or nonlinear. So we would say this is a linear because there is a constant rate of change. Let's take a look at the second table. The increase from 1 to 3 is by 2. From 3 to 5 is also increasing by 2. From 5 to 7 is increasing by 2. And when we're looking for rate of change, we're looking for how much we are adding or subtracting. On y, we're increasing by 26. And then we increase by 125 minus 27 is an increase of 98. Now that isn't the same increase, so this is going to be nonlinear. Because there isn't a constant rate of change. As x increases by 2, y is not increasing by the same amount. Therefore, this is nonlinear, where on table A, as x increased by 2, all of the y values also increased by 2. So here's your turn to look at a couple of graphs, look at a couple of tables, and you're going to determine, do they represent linear functions, and to determine why. So it's your turn to pause the video and to think about, does the table or graph represent a linear function, and explain why. Now that you've had some time, for graph number 1, linear, and the reason why, graph is a line. Graph number 2 is nonlinear. Because the graph is not a line. It is actually what we would call the graph of an absolute value function. Let's look at table 3. The x values are increasing by 1, and the y values are increasing by 2. So this is linear because we have a constant rate of change. Table 4, again, the x values are increasing by 1. Our y values, first one decreases by 8, and it's okay if it decreases. It just needs to decrease by the same amount. But then the next one decreases by 4, so that's not a constant rate of change. So we would say nonlinear. No constant rate of change. Here we have a number of equations, and we need to determine if the equations represent linear functions. Now remember, in order for an equation to represent a linear function, it needs to be able to be written in the form y equals mx plus b. So even if it's not in that form to begin with, can we write it in that form? So I'm just going to shift some things down and add some labels to my screen here. Going to make a linear and a nonlinear. And it might be easiest to find the ones that are not linear, the ones that aren't going to fit y equals mx plus b. For example, I see x squared. Is there an x squared in y equals mx plus b? No, there isn't. So that's going to be a nonlinear function. Also, in this equation, y equals 2 over x is in the denominator. But is x in the denominator of y equals mx plus b? No, it isn't. So that's also nonlinear. We have y equals 3 to the x. X is in the exponent. Is x in the exponent anywhere in y equals mx plus b? No, it is not. So that also makes that nonlinear. Then I have 3 left. This one right here, y equals the square root of x. Is there a square root in this symbol on my x, or in this equation on my x? No, there isn't. So that makes that function, that equation, nonlinear. Now, if I look at these other two, can I write them in y equals mx plus b form? Now, you might say, well, there's no x in this y equals 2.8. But it is a linear equation. It happens to be the equation of a horizontal line, and I'm going to show you something. I can rewrite this equation as y equals 0x plus 2.8. 0x is the same thing as 0. Add it to 2.8 and I have 2.8. So I can write this equation in this form, which makes that a linear equation. And with y equals 6 times x minus 1, if I distribute the 6, my equation becomes y equals 6x minus 1, which is in the form y equals mx plus b. So that is a linear function. That is a linear equation. So these two equations are linear while everything else here is nonlinear. So here's your chance. Which equations are going to be linear functions? I'm going to let you pause and think about which ones are linear. Now that you've had a chance, hopefully what you've decided was, well, x is in the exponent. Here we have x squared, and here we have a square root, so those get thrown out. With y equals 5x, I can write a plus 0, so that puts it in the y equals mx plus b form. So that makes this one linear. And x minus y equals 12. I could add y to the other side. So I'd have x equals 12 plus y. But then I could subtract 12 from both sides and have x minus 12 equals y. And remember, if you don't have a coefficient on a variable, that's a 1. So another equivalent form of x minus y equals 12 is y equals 1x minus 12, which is y equals mx plus b. So this is also a linear function. So we now have seen 3 different representations that we can use to represent functions. So we have in words, an output is 3 more than the input. Remember, the output is the y, and the input is the x. So when I write an equation to go with this statement, I can say y equals 3 plus x. x, or y equals x plus 3. They are equivalent. I can use an input-output table to represent that. And let's just pick some values for the input. Let's use -1, let's use 0, let's use 2, and let's use 3. So I would use these values, put them in for x to get my output. So -1 plus 3 is 2. 0 plus 3 is 3. 2 plus 3 is 5. 3 plus 3 is 6. And I can take this input-output table and make it a mapping diagram to show that we have a function. -1, 0, 2, and 3 were my inputs. Their outputs were 2, 3, 5, and 6. And then I can map that -1 as an input has an output of 2, 0 has an output of 3, 2 has an output of 5, 3 has an output of 6. And to graph this, I can plot the points. I can plot the ordered pairs. So -1 and 2, 0 and 3, 2 and 5, 3 and 6. And if I've done this well, I will have a line, I will be able to draw a line right through all of them. And because it's a line, I should put arrows on it. Because I didn't put all of the possible values of x that I could into the table. So the points on this graph are the points that I used in my input-output table or my mapping diagram. The line itself represents all of the possible points I could have used. So we've got equations, we've got input-output tables, we've got mapping diagrams, and we've got graphs that we can use to represent linear functions.